Welcome to Python Basics with AJD. Still talking about Python packages. We start looking at some very basic and very vital packages in Python. And we're starting with NumPy. I mean, we talked about NumPy, I think, in the last video. So NumPy is particularly good for array computing. NumPy for array computing. So when you work with arrays, we've seen data structures, Python data structures, data types, data structures, and everything. But array computing gives you a bit more power than what you can achieve with those ones, right? So interestingly, some of those Python structures are the things you actually bring here to convert to NumPy arrays and all that. Okay, so NumPy for array computing is what we are looking at. And by way of introduction, NumPy is the core library for numerical and scientific computing in Python. It is the core. So it provides powerful tools for working with multidimensional arrays, what you can call ND arrays, and then performing vectorized operations, fast element-wise computations without explicit loops. We talked about control flow, talking about looping, while loop, for loop, and all of those kind of loops. But with NumPy, you can actually have vectorized operations that are faster than when you use loops. So NumPy is also good for implementing linear algebra, random number generation, and statistical functions. So it is built in C under the hood, right? It's more like the back end is in C, although you are working with Python, right? So this makes it highly optimized compared to pure Python lists. So when you work with Python lists, they can be slower. But when you work with NumPy, because it is built on C, things get done faster. So let's go straight and start looking at the possibilities. Of course, I think under scientific computing, I zoomed in a little bit more to look at some components of NumPy step by step. So if you need a more robust understanding of NumPy, you want to check the scientific computing playlist for that. All right. So arrays, vectorization, and broadcasting. So first of all, we can talk about NumPy arrays. That's ND array. So unlike Python list, NumPy arrays are homogeneous. All elements have to be of the same type. Python list, you can have Boolean, you can have integer, you can have float, you can have everything mixed together, right? But for NumPy arrays, they have to be of the same element. If you're dealing with Boolean, everything has to be Boolean. If you're dealing with integers, everything should be integers, right? So you have to provide efficient memory. So NumPy provides efficient memory storage and computation. So let's look at first, and of course, since this is not me trying to teach NumPy into depth, it is just me introducing you to the NumPy package. And since we're talking about packages, not Python packages, right? So of course, if you did not have NumPy installed, the first thing you have to do is to install it using okay, let me try to create this. So the first thing you have to do is do pip install NumPy. That's the first thing you have to do. So of course I have it installed, so it will just tell me, okay, it's telling me to manage sessions, so I can do that. So anyone I'm done with, I can close all of this. Yeah, so that's done. So with pip install NumPy, okay, with pip install NumPy, I can just run this, and because I already have that in the first place, oh, it's which sessions again? Too many sessions. Thought I was managing them already. Okay. Oh, I should have terminated, not close. I should terminate, then close, right? Okay, I guess we should be good now. Okay, so pip install NumPy. So I try to run this now. So, I mean, those ones are interfering with the resources being used here. That's why this one, I was getting that prompt. So now those ones are terminated, so I already have it installed, so it won't take so much time. Right? So, and if you are doing it for the first time, it may take longer than what you're seeing here. So no worries. So if you have never used NumPy, so the first thing you want to do is to pip install, or any library for that matter, pip install the library, pip install NumPy, pip install matplotlib, pip install whatever. All right. Pandas, yeah. So imagine you want to import NumPy as NP. So you have array. So of course, NumPy is good. It's for array computing, basically. So you have np.array 1, 2, 3, 4, 5. So this is a one-dimensional array. because everything is in. So you're converting a Python list into an into a one-dimensional array. On the other hand, we can have a matrix, which is a two-dimensional array. So in this case now, you have a list of lists. So it is a list, this is a list, but then you have the two in a list. So in that case, it now becomes a two-dimensional array or a matrix. Then you can also have zeros, a 3 by 3, zeros 3 by 3. You can have ones 2 by 4. You can have a range from 0 to 10 following steps of 2. That's 0, 2, 4, 6, 8, like up to 10, like that. Then you can also have linked space. So it's going to divide 0.1. Of course, this is 5, right? But it's going to divide it to, because this is 5 it's going to divide it to 4 equal portions, meaning that you are going to have jumps of 1 over 4. That's 0.25. So you have 0, 0.25, 0.50, 0.75, and then 1 itself. So, and then line 10 is us printing everything out. So you want to have this one-dimensional array followed by the matrix 1, 2, 3, 4 in row 1, 1, 2, in row 3, 3, 4. And then you have the zeros 3 by 3, 3 rows, 3. Well, maybe 2 by 2, but let's see when we run this. One's 2 by 4, then a range just like I've explained. So we run all this now. Okay, see how it goes. So we have this is a one-dimensional thing. 1, 2, 3, 4, 5. We have this. This is matrix 1, 2, 3, 4, like I said, and we have zeros. 3 by 3 zeros. So you have 0, 0, 0 in 3 rows, and then you have 2 by 4 ones. So that's 2 rows, 4 columns. So you have all ones. Then for the range now, you have 0, 2, 4, 6, 8, because we are moving from 0 to 10, but the time step is 2, or step length as they call it is 2. So you have 0, 2, 4, 6, 8. And now this is 5, right? But we are going to have this in 4 divisions. I mean, in jumps of 1 over 4. If it was 7, it would be 1 over 6 jumps. So that's why you have 0, 0 0.25, 0 0.5, 0 0.75, and 1 finally. All right. For vectorization, you can perform element-wise operations without explicit loops. So it uses C-level operations, and it is much faster than Python loops. For instance, so you have your data, and then you want to turn this Python list into a NumPy array with variable name data. So you have np.array 1, 2, 3, 4. So it's into a NumPy array called data, and then you want to square each data. So just a data star star two. So it means you are squaring each element in this data. All right, and then so running this squared now just is 1 squared 1, 2 squared 4, 3 squared 9, 4 squared 16, like that. Then for broadcasting, so it allows operations on arrays of different shapes without explicit replication. So it's a very fast way of getting things done. So you have a NumPy array with variable name A 1, 2, 3, and you have B is 2. So if the result is A plus B, so the broadcasting now, instead of having to say, so this 2 now, you're adding every element in the array to 2. So you have 1 plus 2, 3, 2 plus 2, 4, 3 plus 2, 5. If you print the results, you get 3, 4, 5, like that. All right. So that's broadcasting. Then we also have indexing, slicing, or reshaping. So for indexing, right, you want to access elements using row by column notation for two-dimensional arrays. So imagine array is, you turn a list of lists, which is a two-dimensional array now, into a Python, into a NumPy array, right? So in this case, now if you want to print 0, 1, of course, Python counting in Python starts from 0. So 0 means 1 and 1 means 2, basically. So it means we need something in row 1, column 2. So, and row 1 is 1, 2, 3. Row 2 is 4, 5, 6. So row 1, column 2, that would be 2 in this case now. So if you run this now, you just get that 2 right here. All right, I've done this more depth under scientific computing. Then talking about slicing, you want to extract subarrays by selecting rows, columns, or ranges, right? So in this case now, you want to print. So, indexing is you referring to a particular item, but slicing is you cutting off a portion of the list, for instance. So still dealing with this kind of array now. We need, this array now, that's, so this is everything in the second column. Everything in the second column, basically, this is what this is about. So because we don't care about the row, so the row can be anything, but we need everything in the second column. So in the second column, we actually have, because this is 1, right? And we have 0, 1. So 1 stands for second column. So second column here will be 2 and 5. And that's how you're going to get 2 and 5. Then here you need everything in the second row because we have one comma. We don't care about the column now. So everything in the second row, and second row is 4, 5, 6. So if you run this now, you get 2, 5, and 4, 5, 6 like that. So when you have full column like this, it means we need everything in that portion. So if it's coming first, that's everything in that row. If it's coming second, that's everything in that column, like that. Then we also have Boolean index, which is powerful for filtering with conditions. So if you want to filter based on certain conditions, so you have array, which is np.array. You have a list 10, 20, 30, 40. So here now, if you want to filter, so you say from this array greater than 20. So you want to extract everything in the array greater than 20, and then you now use the array to reference it again. So it means you're going to have just 30 and 40 in that case because they are greater than 20. Then you have reshaping. So you can change shape. You can change the array without copying data, right? For instance, you have arrays np.range. Now, anytime you have this range like this, it means you're moving from 0 to 11, right? So, and that will still be 12 items, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 12, starting from 0. So, well, you don't get to the 12 as we know already. So, because you have 12 elements, you can reshape this into 3 rows, 4 columns, right? So we run this now. So you have 3 rows, 0, 1, 2, 3, 4, 5, 6, 4, 5, 6, 7, 8, 9, 10, 11. Of course, we can do the same thing. Again, we can have, okay, if I do alternate enter, it opens a new cell. And then because it is 12, right, we can use multiples of 12. I can shape it into 4 by 3. I can shape it into 4 by 3, right, like this. I can so that's 4 rows, 3 columns. I can, of course, still shape it, you know, alternate enter, and I'm creating a new cell. So we can shape it into 2 by 6, right? As far as it is, the product gives us 12. So 2 rows, 6 columns. We can shape it into 6 by 2, right? We can shape it into 6 by 2. 6 by 2, right? We can have that. We can shape it into 1 by 12, right? As far as you can get a product of 12, you can shape it into 1 by 12. That's now a just one-dimensional array. So you can also shape it into 12 by 1. All right. That's 12 rows, 1 column, like this. So that's now like a column vector. So you can do all of that. Then we can also use NumPy for linear algebra, random numbers, and statistical operations. So talking about linear algebra now, of course, I've dealt with this in depth in under scientific computing. So use NumPy linear algebra for matrix operations, eigenvalues, etc. So imagine you have you have declared. Of course, we already know how to declare a matrix. So I just have a list of lists. So then it becomes two-dimensional. So you have matrix A is 1, 2, 3, 4. Matrix B is 2, 0, 1, 3. And then you need the dot product of that. That's you need the dot product. You need the transpose. So for transpose, you just have. So for dots, you need numpy dot comes from numpy, then a comma b, so it will get you the dot product of this. For the transpose, you just need a dot t, so it will transpose the first row is 1, 2, it becomes first column 1, 2. So you're going to have 1, 2, 3, 4. That's in the first row you have 1, 3, and then you have 2, 4, like that. Then you get the inverse, you get the eigenvalues and the eigenvectors, and then in line now you run all of these things. So you have the array. Of course, you have the dot product now gives you this array. So that's like this is the dot product. You have 4, 6, 10, 12. Then the array, the transpose now you have 1, 3, 2, 4, like I said. And for the inverse, this is the inverse, right? So that's minus 2, 1, 3 over 2, minus 1 over 2, like that. And then for the eigenvalues, you have minus 0.372, 5.372. And for the eigenvectors, you have this last one here. Then you can generate random numbers, right? So if you can generate random arrays from different distributions. So if you have this variable in random array and you want to generate a 3 by 3 random array, you want np.random.rand. So in that case, you want a uniform thing from 0. 0, it doesn't go less than 0, but it goes as far as anything short of 1, because you have this interval closed down and open up, so it doesn't get to 1. but it doesn't go below 0. That's what that implies. Then you can also do a so you see this is np.random.rand. So that's uniform distribution. But then if you have np.random.randn, that's normal, a standard normally distributed random numbers. And then you can also have integers. Maybe you want integers from 0 to 10 and you want it to be 2 by 5. Of course, that'll be like 0 to 9, and that's still 10, right? So you can do 2 by 5, 5 by 2, and all that. 1 by 10, 10 by 1. Then here in line 5 now, this means we want to run random array, normal and integers. And I have all this now. So this is 3 by 3, as you can see. So you can see none of them gets to 1, but none. So they are all between 0 and 1. From 0 to 1. There's no 0 specifically, but 0 could have been part. I mean, because they are random, right? Each time I run, they're going to keep changing, right? And that's why whenever you want to use random numbers and you don't want things to keep changing, you need to use a random seed, a seeding of 42 or whatever you choose. All right. So this is 3 by 3, standard number. So all this will be normally distributed with mean 0 and standard deviation 1. And then for integers now, so we just want integers from 0 to 10, right? So like that. So if I keep running, I keep getting different values. Now, what if you are in a class and you want to use matric numbers to decide who gets a particular prize, right? Who gets a particular award, okay? So, and you want it to just be a random thing, right? So you can just simply use this, right? So you have np.random.randint. So rand n is normal distribution. Normal rand is uniform distribution. Rand n is normal distribution. Rand int, that's for integer. So maybe the matric numbers are from, say, 6 to 6420. So say 6688, right? So, and you just want to, it's more like draw a kind of raffle draw. You can even do use this for raffle draw. So you maybe you have 10 gifts. So you just run this 10 times. Each number that shows up, you give the person. So if I run this now, okay, is it not supposed to show what's happening here? I don't know. Integers. Okay, maybe I have to print, right? I guess I have to print. Do I have to print? Do I really have to print? We didn't print. Oh, okay. Yes, I forgot. I have to print here integers. I just type integers. So you see, we run a 6475. So this first person gets the gifts. You run it again 6658. You run it again 6548. You run it again 6622, 6512, 6444. So that's if you want to generate random numbers, you can always do this, right? 6042, 6516, 661, 6439. So you can keep going like that until you are done. So so there's no need for raffle draw again. Just get the numbers and you can do this random thing. Okay. So statistical operations, you can compute mean, standard deviation, median, etc. So imagine you have this data. You're making a Python list containing 1, 2, 3, 4, 5 into a NumPy array, and you want to calculate the mean of the data. The variable name is mean, so you just have np.mean of the data, standard deviation np.std of the data, median np.median of the data, sum val np.sum of the data. Then you print mean, std, median, and sum val. You run that, and you get all your results. This is float 3.0. This is float 64, 1.414, blah, blah, blah. Then 3.0 is the 3 is the median, right? Because it's already arranged, so 3 is in the middle. Then the sum, you add everything of 5 times 6, 30 divided by 2, that's 15. All right. So you can perform optimization with NumPy. So for instance, you can have vectorization versus loops. So if you want to avoid Python loops, we talked about looping the other time. If you want to avoid Python loops and you want to prefer vectorized number operations, so you can see that this takes less time. So if Python loops are slow. Imagine you want to result from, you want to square every value from X in range 100. This is 1 million. That's a lot. So I'm not interested in the results. I just want to see the time it will take. And for you to see that, just do percent time it. So it will show you the time this takes. So this runs. This runs and runs and runs and runs and runs. And then it outputs the time. So it takes 93.3 microseconds and plus or minus 13.8 microsecond per loop. Okay, if I run it again, let's see, it's the same thing, I think. So see the time it takes, it keeps going, 93 microsecond, point something microseconds. So now it's 97.1 microseconds, like that. So with all this information. But then that's when you do, you are squaring every number from 0 to 1 less than 1 million. But then we are doing the same thing here, but see, so instead of doing a loop, we have a for loop here for x in blah, blah. But here we just have vectorization. So we have array equals np dot a range, same 1 million. And then we are doing the result, array raised power 2. So we run that, exactly the same thing, but then this one takes only 2.03 microseconds, plus or minus 83.9 microseconds. So, I mean, this one is, even the plus or minus is microsecond, but this one, I mean, it's milliseconds rather. So this is 97.1 milliseconds. And here we have 2.03 milliseconds, plus or minus 83.9 microsecond per loop. So you see how vectorization, so you can avoid looping for vectorization. That helps a lot. Okay, and that's made possible by NumPy. All right. So imagine you can also broadcast instead of manual expansion. If you imagine you want to replace nested loops with broadcasting for speed, so you have a NP range 3 reshape 3 by 1, right? NP range, a range 3 is going to be like 0, 1, 2. So you have 3 elements that you are reshaping into 3 by 1, and then you don't want to add that to NP range 3. That's just 0, 1. That's just 0, 1, 3. So, okay. And we are printing by saying A plus B, right? So, okay. So here, this is 3 by 1. So we are adding each of the elements. So here we have 0, 1, 2, right? So, and here we also have 0, 1, 2. So it means you're adding 0, 1, 2 to everything. So you add 0 to the first one, and then you now add 1 to the second. That's why you have 1, 2, 3. Then you have add 2 to this. That's why you have 2, 3, 4. So you can broadcast instead of manual expansion. So that's quite efficient. So then we also have memory efficiency, right? You can use appropriate data types to save memory. So imagine, well, in fact, I can even say, so that I don't confuse you, let me just call this array 1 and call this array 2. These are mere variable names. Array 1, array 2. The only thing is that their data types are different. This is array 1. Okay. This is array 1. And this is array 2. Okay, that's all. And then I have array 1. And this is array 2. Okay. So imagine for array 1, we have 1, 2, 3, and we want it to be integer 8, and then array 2 wants it to be integer 4, integer 64 rather, right? And then I want to see the kind of how much time each one of them takes, or how much memory space. We're talking about memory efficiency. They say integer 8 takes just 3 bytes, and integer 64 takes 24 bytes. So if you specify the kind of array you want, it can actually save memory if memory is really of importance to you. Then we also have in place operations, right? So you want to avoid extra memory allocation by modifying arrays directly. So if you have array equals np.array 1, 2, 3, 4, 5, right? Turning this Python list into a NumPy array, all right? And you want to multiply each one by 2. So you have 2 ways. You can actually create a new variable and assign and then now see that new thing multiplied by 2. Like in this case, in fact, maybe this should come first. So imagine you can have indirect multiplication where you have new array equals array times 2. So that'll be, in this case, you are using extra memory allocation. So if you run this now, you get 90. So it takes 96 bytes. But but here now, instead of having to create a new memory, you just have array star equals 2. That means just multiply whatever you have by 2 and assign it back to array. Okay. You see, this one takes 40 bytes. Doing it directly takes 40 bytes. And then doing it indirectly takes, this still takes 40 bytes. The first time I did it, it took 96 bytes or something like that. So, I mean, the list is that they are the same, but this one can actually go more than that, right? So, and then we have profiling tools. So you can use, I mean, we saw a case where we had to use percent time it to know the time a particular operation takes. So in this case, you can use percent time it in Jupyter to measure execution speed. All right. So again, we have ARR equals np.a range from 0 to 1 short of 1 million, and then you are squaring that. So the other time we saw the percent time, it's coming at the head, but here we have it coming just on the same line with the execution. And that takes a bit of time because we are dealing with 1 million. So we are squaring every number from 0 to one step short of 1 million. And this takes just 1.01 microsecond plus or minus 34.8 milliseconds, right? Plus or minus 34.8 microseconds, like that. So, I mean, that's the beautiful thing about NumPy for array computing. So with this, we'll come to the end of this video about NumPy for array computing. Let me know how helpful this is for you. And if there's something you'd like me to try, feel free to let me know. If you have not subscribed already, you are missing a whole lot. So why not go ahead, subscribe, hit the notification bell so you can always get alerted each time a new video is released. Of course, now that you're subscribed, thank you. But you can take it a step further. You can click on join and become a member of the channel. And that comes with some special privileges. I think I'm beginning to have members already. Interesting. You want to join them. So feel free to join them so you can get some special privileges. As you click on join, you find all those privileges right there. Ultimately, don't forget to like, share, comment so that more people can have access to this great content I have going on here. So come your way again. Keep doing Python right. Bye.